Okay, maybe we can start today's session. Uh, okay. Hello everyone. So I'll just share my screen. Give me a second. Yeah. Yeah, just give me 1 minute. Okay. Yeah. So hi everyone. So my name is Zenia. Welcome to week 9 of these problem solving session. So by now you are familiar with our format. Essentially, we have this format where we are trying to recap the week's lectures and also to get more of an idea of what is happening right now, right? Right now we are, as mentioned, we are in week 9. So we are well within the course. You have learned many things about the standard model and the associated physics. You've learned about how the particles are given a specific character. Based on the specific character, they can be mathematically described in terms of group structures. So that's why group theory is very important. It's the grammar of the standard model. And similarly, you saw about how based on the group behavior, we can also look at how the groups based on the group behavior we can infer certain physical things. For example, when a group symmetry is broken, we notice that this very interesting thing, which is Goldstone's theorem, comes up, and we saw about how to describe continuous symmetries in terms of Lie groups, and how breaking continuous symmetries can lead to a mass being produced in the standard model. For example, in the form of the Higgs mechanism, right? So that we saw about electroweak symmetry breaking and so on. So we've kind of described a lot of things that come up naturally in the standard model. But as we mentioned previously, the standard model is not the complete picture of what we have in particle physics, right? Standard model is very successful. It's the most successful theory we have, but it still doesn't explain everything. And one of the things that it doesn't explain is neutrino oscillations. And today we'll be actually focusing on neutrino oscillations. And you'll see how, in order to explain neutrino oscillations, we need a critical ingredient, which is that neutrinos actually are massive particles, which is not the case, which is not what is predicted by the Standard. Okay, so we'll start to look at the PMNS matrix, neutrino oscillations, and how the different kinds of neutrinos, that is the solar and atmospheric neutrinos, can actually tell us about what's happening. But in the meantime, yeah, just to get an idea of, this will be the very first start of what is called beyond standard model physics that we'll be looking at in the course. Okay, so these were the notes that I used when I was preparing for this week's lecture. So all of them have lots of different interesting aspects of neutrino physics. I think that if you guys are interested in this subject, you can start with this textbook, but these are all different notes that also collect some of the writings on this subject. Okay, okay, fine. So, to start, before we go to neutrino physics, let's just finish off our discussion on the CKM matrix, right, which we had last time. So last time we spoke about how the CKM matrix shows us about quark mixing, and that kind of also tells us about the what can I say, the motivation that brings us towards the PMNS metrics in the first place, right? Because the question was that if there is such a mixing in the quark sector, can there also be mixing in the leptonic sector? And that's kind of the question that the PMNS metrics is trying to solve. Okay, so but before that, let's just wind up our discussion of the CKM metrics. So as we saw last time, the CKM matrix is a mixing matrix. You imagine that it takes you up quark, the up type quark, which is the up quark, the charm quark, and the top quark, to the down type quarks, which are the down quark, the strange quark, and the bottom quark. So this kind of relation between them is what gives us the CKM matrix, right? And you can write this as a sort of a complex rotation in 3 cross 3 flavor space, and that's when you get this kind of matrix, which is what we call here. Now, the important point here is that the matrix is unitary, right? It preserves lengths. Unitary means it has length of 1, so you know that it preserves the length of the matrix, and that's what unitary means here. Okay, so here the idea is that we preserve we put in the unitarity of the matrix, which again you can also tell that it's a unitary matrix because of complex rotations, right? Whenever you have a rotation only changes the angle. If you think of a normal rotation, even in a plane, the rotation can only change the angle. It doesn't really change the uh, it doesn't really change this thing itself, the length of the vector, if you rotate a vector. Similarly, that's why we need a unitary matrix always describes rotations. So from this unitarity condition, we can get, if we just equate and do the matrix multiplication, you find that there are 9 orthonormality equations. Of course, you can also write it in terms of the Wolfenstein parametrization. That's a different discussion. But basically, this equation, this kind of equation, right, where you have something like uh, the equation which is given here, this basically corresponds to having a triangle in the complex plane. Okay, so that's what this is showing. And again, the lengths are here given in terms of the Wolfenstein parametrization. That's why this a lambda cube etc is given here. Okay, so, okay, fine. So this is the idea behind the Wolfenstein parametrization and the thing. So, okay. Okay. So now, if we normalize the triangle in the complex plane, we normalize it by its length. Basically, you can divide it by some factors and you just take the ratio. Then this gives you an idea of renormalizing the horizontal scales. So just normalize by dividing one of them, by dividing by this term throughout, right? So this becomes 1 and this becomes this. So this allows us to find the area. So these are the different ways in which this is parameterized. So the idea is that there are these 9 orthonormality equations, and we know that finally it corresponds to 4 degrees of freedom. 3 are the real Euler angles, and 1 is the phase, and that phase is actually what leads to CP violation, as we saw last time. So these unitarity triangles help us to establish the unitarity of the thing, and as you saw this week, this also leads to an invariant quantity, which can help us to have a basis in independent measure of CP violation. So this is important because till now we have talked about CP violation, for example, in the context of discrete symmetries. At the very beginning of the course, we spoke about CP violation in terms of the K mesons, right? So K and K0, all those different kinds of mesons, we spoke about the CP violation in that context. We are speaking now about CP violation in the context of CKM metrics, but these are all tied to some basis or the other. It's either tied to the basis of the K mesons or it's tied to the basis of the quark mixing. We want a basis independent quantity or an invariant to be constructed. So the construction of the triangles in the complex plane in this fashion helps us to form this invariant quantity. And this is what is called the Yarlskog invariant, J. Okay, so the CP violation can be directly, you can show that CP violation, that is the existence of this phase, directly gives us non-zero unitary triangles. That is, the triangle area becomes non-zero. This you also showed in your class. And the triangle area actually becomes an invariant, and that is what we call the Yarlskog invariant. So this is something you saw last time, which is that the CP violating phase existing in the standard model is directly tied to how many quark flavors there are. Right? You can see that if there were only 2 quark flavors in the universe, or two, sorry, not flavors, how many quark generations there are. If there were only 2 quark generations, no top and bottom, only up, jump, down, and strange, you can see that there's only one free variable. All the other variables get kind of you can basically do transformations and they go away. So based on the conditions like orthonormality and the three quark phases, it goes away. You're only left with one free variable. So everything can be parametrized instead of one real variable. So there's no CP violating phase. Whereas in this case, we saw that we need four parameterization. So we need three Euler angles plus one CP violating phase. And that's why three generations is the minimum particle content to generate CP violation. Okay, so again, the idea of how large is the CP violation, again, we have kind of measured it in terms of the K mesons and or in terms of the CKM matrix itself when it's parameterized in different ways. But if we really want a basis independent measure, we can have the Yarskog invariant. So you can see that CP violation requires three generations with non-zero quark masses. So this is a condition. And this is the Yarskog criteria, which basically boils down to taking the triangle's area, right? So this complicated looking term is what it looks like. You can also write this in terms of, you can see that it all depends on the difference of square masses of the different quark flavors. And you'll see that whenever we have this sort of flavor mixing, right, then this kind of difference in masses squared is or difference in, not difference in masses square like m1 minus m2 squared, but difference in the squared masses, so m1 squared minus m2 squared. This is common when you have flavor mixing in a unitary sense in the standard model. This is what we see during neutrino oscillations as well. So this is Cecilia Yarskog. She is the person who gives her name to the Yarskog invariant. And as I said, this gives us a basis independent way to establish the amount of CP violation in the standard model, which is very important because the amount of CP violation in the standard model is tied to, for example, the strong CP problem, right? Where we think the strong force should also violate CP, but we find that the violation is either non-existent or a very small violation is there, which we don't really understand. So what allows CP to be somewhat preserved in the strong interaction is not well understood. Okay, so this you saw, this is from your lecture notes. So here you can see that this is basically about CP violation in terms of unitary triangles. So you can see that the K meson oscillations give you a CP violation of around 10 power minus 3. Again, we discussed this way back in the first week. Similarly, CKM matrix gives you a CP violating angle or phase of like 69 degrees in the quark sector. But if we want a basis independent measure, we have to take some combination of parameters. That is exactly what's been done here. It's just written in terms of different values, but basically the same thing in terms of the quantities that come up in the unitarity triangles. And if you write it in terms of your usual CKM parameters, it comes to be like this. And you can see that if delta is 0, J goes to 0, and that tells you immediately that this is a measure of CP violation. So in the lecture 42, if you see, there is actually proof of how the area of the unitary triangles are all equal and they are also invariant and give you the measure of CP violation. You can go and check it out yourself. Okay. So the important thing is whenever we construct the unitarity condition for the CKM matrix, just by doing the experimental observations of the various parameters of the CKM matrix, we can then construct this Yarskog invariant, and from that we can get a measure of what is the level of CP violation that exists in the standard model. Okay, and all these triangles have the same area, so you can choose whatever is easiest to measure. Usually that is in terms of the up and down, up quark and other things. Okay. Okay, fine. So then the question naturally comes that we have looked at quark mixing till now in terms of the CKM matrix. Then what about leptons? So as we discussed last time, for the charged leptons like electron and proton, sorry, not proton, electron, for example, the charged leptons like electron, muon, etc., we actually do have good measurements of them. Their mass and flavor basis are the same. We don't really have these two problems where we have one mass basis and one interaction basis, because they have well-defined masses, right? We do have an eigen basis in which we measure them and we routinely do experiments in them. With quarks, it's complicated because we cannot separate the quarks because of asymptotic freedom. They're always confined within protons and neutrons, for example. And similarly, you'll see that similar kind of philosophy comes with neutrinos. So with neutrinos, the kind of the analog analog of the CKM matrix in the lepton sector arises for neutrinos particularly, which is a PMNS matrix. So with neutrinos also you have these two bases. So for quarks, remember the two bases were like the interaction basis and the mass basis, where one, each has a different interpretation. Interaction basis where the weak force acts, mass basis when we diagonalize the mass matrix. Similarly, the PMNS matrix also, there are two kinds of bases. One is the mass matrix and the other is the flavor basis. So depending, you can see that the different mass bases, usually mass basis is denoted by numbers. So you can see that the different masses are actually different, what can I say, mixtures of the up down sorry, I'm saying up down, electron muon and tau. Okay, so they are different admixtures of the electron muon and tau. You can see that they have this kind of mixing, and you can see that where in the CKM matrix we had an approximate structure. You can see that these entries are very nearly one, this diagonal is very small, and so on. And that's why Wolfenstein was able to somewhat parameterize it. There was a high degree of symmetry, right? These values are somewhat similar, for example, and so on. Whereas that kind of structure is not present in the neutrino sector, so we are not able to reduce it to some neat parameterization like the Wolfenstein parameterization. And neutrino oscillations or flavor induced mass change, sorry, mass induced flavor change was only really figured out, or experimentally established in 2001. So this is a very young field comparatively. People are still figuring out things about neutrino oscillations and how they behave. So we'll try to see a little bit more about it. So these are the experimental values of the PMNS matrix we have so far. And from that, we get an idea that the neutrino has a mass. So remember, I told you that when you have these unitarity and mixing matrices, it comes out naturally, even in the CKM matrix, that they depend very closely on different masses of the different flavors. Then only they can oscillate between each other, because basically the different masses correspond to different momenta. So as the wave function or the state of the neutrino is evolving, the different mass bases, or the different masses evolve at slightly different rates. So what happens is a flavor is kind of a mixture of these different masses, because they all evolve at slightly different rates. Once you measure after a given time, the original mixture, which would have been something like this, could have evolved to something like this, for example, if you invert this and write this in terms of the electron muon and tau. So that's the idea here. The idea is that we need masses for the neutrinos, and we also need different masses for the neutrinos. So this is very important, because as I said, or as we have been seeing till now, the standard model of particle physics assumes the neutrinos are massless, right? In the Higgs mechanism, the neutrinos do not interact with the Higgs field. You see that the Higgs mechanism does not give them mass. So the fact that the neutrinos are massive hints us towards the fact that the standard model is not complete, and we actually do need some beyond standard model physics, some new physics, in order to explain these scenarios. Okay, so if you see, the thing is that the neutrino masses are actually very small when we compare with the normal other constituents of the standard model, right? So you have the gluons, the WZ bosons, the Higgs, the top, bottom, all the different quarks, electron, muon, tauon. You can see that they all are, from around, the electron is of course the lightest, being 500 keV or so, and then all the way up to a few times 100 GeV or so is the maximum, right? The Higgs boson is 125 GeV, as we saw last time. The W and Z are around 100 GeV. So basically all the particles that we have in the standard model are concentrated around MeV to GeV still. KeV to, let's say MeV to GeV, right? The electron is 0.5 MeV, for example. So this is how it is. On the other hand, you can see that neutrinos are completely different, right? Neutrinos are at the milli electron volt scale. So they are so very light. And this is probably why us treating neutrinos as massless has not been a problem for most of physics, right? Most of the physics that we do is perfectly done by assuming neutrinos massless, because neutrinos mass is so small when we compare to other cases. But nevertheless, it does have a mass. So not having a mass and having a mass are obviously very different physically, even though magnitude wise it's a very small particle. Okay, so this is, and the other important thing to note here is that neutrinos are really abundant in the universe, right? So for example, this is a picture of the sun at night. Okay, so obviously at night you don't have, your usual visible spectrum that you see because the sun has set in the sky. But basically this is a picture taken by Super Kamiokande which shows the neutrino flux coming from the sun. The new picture was taken at night, so the sun rays are not coming overhead. They're coming, the neutrinos are actually traveling to the earth and coming to us. The sun is on the other side of the earth because it's night, so the sun has set. Those neutrinos from the other side of the earth, at the polar opposite of the earth, have traveled through the earth and come to us. And that is what this picture is showing. So basically, you can see that it looks almost as bright as it does during the day, except that this color is coming from the neutrinos. So neutrinos are so very abundant. There are trillions of neutrinos which are passing through your body, my body right now, right? So they are so very abundant and they are so very non-interacting that it's really difficult to study them. And that's probably why assuming they were massless was okay till now. But obviously, when it comes to interaction, even a very small mass can lead to interaction between the neutrinos, right? Whereas zero mass would lead to no interaction, small mass does lead to enough interaction that we see this kind of neutrino oscillation. So, to illustrate how neutrino oscillations work, you can think of a simple two-flavor scenario. It's easier to think of two-flavor scenario because it's an easier think problem to work out. But obviously, the real situation is that we have three generations or three flavors of neutrinos, which is the electron, muon, and tauon, and all of them kind of interact with each other. So you can see that we consider a simple two-state quantum mechanics system with flavor eigenstates. So these are the flavor eigenstates which are measured in the flavor basis. So electron and muon, and mass eigenstates nu1 and nu2. So remember, when you say flavor eigenstate, it does not have a definite mass, and vice versa, right? Mass eigenstate does not have a definite flavor. So for example, I cannot say that nu e has a definite mass. The moment I measure its mass, I'm in the mass basis, right? I've diagonalized the mass matrix, so to speak. So I'm in the mass basis and that collapses it into a mass eigenstate. The other main thing to understand is that we never observe or prepare or deal with neutrinos in the mass basis ever. We still do not know what their masses are, and we don't interact with them in the mass basis because we know what kind of neutrinos are associated with what kind of reactions, right? Because we know that, for example, in beta decay, if I perform beta decay, I know that the neutrino that comes out of beta decay is an electron neutrino or anti-neutrino, depending on what kind of beta decay you're doing. Similarly, if I prepare something with a muon, I know that there's going to be a muon neutrino or anti-neutrino that's associated with it. So the important thing is that we can control what flavor a neutrino is. We cannot control its mass, and in fact, we have never dealt with neutrinos in the mass basis. But the mass is still important because mass is what makes the neutrinos interact with each other, in the sense that, as I said, because each flavor is composed of different level, it's a linear superposition of different mass eigenstates. Because of that, when we do an evolution of the state, the different mass eigenstates evolve at different rates, and finally the mixture you're left with is different than the mixture you started with, and that's why we say that the flavor change has happened, right? There's a flavor oscillation, in the sense that the neutrinos are not literally oscillating in physical state space. You'll see that it's that probability of being electron or muon or whatever that is oscillating. So it's the probability of being an electron neutrino or a muon neutrino that's oscillating. So the oscillations are actually in probability space. Okay. Fine. So you can see that the flavor states are those produced in conjunction with the corresponding charged leptons, whereas the mass states are energy eigenstates, which energy is equal to mi in the particle rest frame. So because neutrinos are so ultra relativistic, we don't really observe neutrinos at rest, right? They're basically massless, which means they move very, very close to the speed of light. So we can really control the flavor eigenstate. We cannot control the mass state, and we really cannot measure or produce things in the mass eigenbasis. So neutrino oscillations can occur when the flavor and mass eigenstates don't line up. So basically you can see that electron muon. This is cos theta sin theta minus sin theta cos theta, nu 1, nu 2. Suppose a nu e state is created at some time with a 4 momentum p that is much larger than m1 and m2. Later it evolves like this. But you can see that because nu e itself is made of nu 1 and nu 2, there is a different evolution for nu 1 and different evolution for nu 2. The probability to detect nu e at a distance L, you just take, a usual quantum mechanical probability, which is that final state, initial state, you take the bra and kit and square it for the probability amplitude. And you can see that the probability now has this oscillation term, right? Theta here is the theta that comes from your neutrino mixing, which is set by nature, right? We cannot mess with that. That basically comes from your PMNS metrics. On the other hand, the other quantities, you can see that delta m squared. So again, delta m squared is m2 squared minus m1 squared, like how we saw in the quark sector. Similarly, the length through which it has traveled and the energy of the neutrino. All three of these play a role. So that means that if the masses of all the neutrino flavors were same, we wouldn't see oscillation. If it doesn't travel at all, if it's just stationary at one point, then also we wouldn't see oscillation. And if the energy is very small, then also if the energy is very high, we don't see oscillation, right? So these are the terms which tell us about, this is the terms that tell us about what is the oscillation. So remember, the oscillation is of the probability of finding a neutrino in a particular state. The oscillation is not the neutrino itself. Don't imagine that the neutrino itself is oscillating. That's not what's happening here. So the usual way to do this and what you did in class was to take an ultra relativistic limit and do this kind of approximation. This approximation again was explained in the class, and that's how you do this. Okay. And you can see that this is also a line up with if you do a proper derivation using density matrices and so on. So this result illustrates the necessary ingredients for neutrino oscillation. Specifically, the neutrinos must have different masses and the mass and flavor eigenstates must be misaligned. So this theta is basically from this matrix, right? This is like our proto PMNS matrix. The real PMNS matrix, of course, 3 by 3 because we have 3 neutrino flavors and corresponding 3 mass eigenstates. But for our purposes here, because you're doing a 2 flavor approximation, this is our PMNS matrix. And the theta comes from this. So the theta is set by kind of nature, right? Nature tells us that how much is the mixing. Similar to how CKM matrix parameters are not derived from first principles, they have to be taken from nature. So that is what theta means here. So basically you can see that you can see that the neutrinos must have different masses and the mass and flavor eigenstates must be misaligned. When these conditions are met, then the probability to observe the initial neutrino flavor in the detector varies with neutrino energy and detector distance. There's also a non-zero appearance probability to detect the second new flavor, which by unitarity is this. So basically, the original E neutrino, the original E neutrino can either end up as, if we consider just a 2 flavor system, at the end it can either end up as a E electron neutrino itself, or it can end up as a muon neutrino. So obviously, because these are the only 2 possibilities, the probability of an electron neutrino ending up as a muon neutrino is 1 minus the probability of the electron neutrino ending up as an electron neutrino. So this is sometimes called the survival probability of the neutrino, and this is called the oscillation probability of the neutrino. Okay, but it's simple probability here because both of these together should be 1, because the final state of the electron neutrino is that it either may end up as an electron neutrino or as a muon neutrino. So here you can see that this is 1 minus this means only this part of the term survives, and that's exactly what we see here. Okay. So again, this is just a simplified picture to get an idea of electron neutrino oscillations. But of course, oscillations can happen among all three flavors of the standard model neutrinos. The generalization of the two flavor mixing to a full system is given by the PMNS matrix. So this is the PMNS matrix, and similar to how we decompose the CKM matrix into these three rotation matrices and one phase matrix, you can do a similar kind of thing. Here you can see that there are three rotations and one phase, and this decomposition is useful because it may be that different you can see that each one of them is associated with a different angle, and different sort of experiments may pick up different angles, in the sense that mixing between two flavors and not the other, for example. So for example, you saw that in the atmospheric neutrinos, for example, it's mostly muon and electron that we have to consider. There is some tau neutrinos also, but that gives us more of a handle of those, the mixing between those two flavors. That's the idea. Okay, so for example, the theta 1 to 35-degree angle is determined best from measurements of neutrinos emitted by nuclear reactions in the sun, sometimes called the solar mixing angle. Neutrino obtained from cosmic ray showers in the atmosphere gives the first good determination of theta 2, 3, which is called the atmospheric mixing angle. And there's some other thing. So here we can't really say if this is electron muon or muon tau or something like that, because these are in terms of the mass eigenbasis, right? So as I said, if it has a definite mass state like nu1, nu2, nu3, then it does not have a definite flavor. So then we cannot say that it has this definite flavor. So that's why maybe the previous statement I made is slightly wrong. What I meant is that by parameterizing in this way, we can isolate particular mixing angles, but we cannot really then put it in terms of some particular state, some particular flavor of the neutrino itself, because now we are in the mass basis. So from oscillation measurements, you also get the mass differences. So remember when we write delta m squared like this, sorry, this means m1 squared minus m2 squared. So you can see that again, the value is very small. Some small number shows you that the difference between the neutrinos. So again, we don't have a good idea of what is the masses of individual neutrinos. The only thing we have an idea of is what is the mass difference between two neutrinos. And one of these comes from solar measurements, which I'll talk about at the end of today's class. And the other comes from the atmospheric cases, which you saw in today in your week's lectures. So again, oscillation with three flavors. If we do a similar kind of, writing everything down here, of course, the challenge is that now instead of just, writing in terms of a linear combination, we actually have to take into account that this is a matrix equation. So you'll have to write it in terms of different matrix components and so on. But if you do the same kind of calculation, you can get this as a probability amplitude for a particular flavor alpha to go to beta. And if you take a limit in which the delta m squared L is much, much less than E, so these terms are much, much less than 1, then you get this as the value. Okay, because you use unitary, you have this condition, and finally you get this as a value. So this reproduces your two flavor result. So your if you set one of the mass differences to close to 0, you're essentially you're reproducing the two flavor result. Okay, so I just wanted to, before we go to the questions, show you how these oscillation experiments are actually done. So I'm telling you that mass is measured, length is measured, but how are they actually done? So this is a video by Fermilab, which is one of the big particle accelerators in the US. They have also planned an experiment to be coming in the upcoming decade or so, which is called DUNE, which is meant to be a facility where you can study neutrinos and their various properties, including their oscillation. So here they talk about how oscillation experiments are set up. So this Fermilab has a bunch of videos on neutrinos which are very interesting. But I just thought that one of the videos I'll show you today, because it's directly related to how oscillation lengths are measured and how we can actually tell what is the difference of masses and other. So I'll just play this video.
Imagine you're running a marathon. You high-five someone at the first mile marker and they see you as a human, normal. You high-five someone else at the 10-mile mark, now they see you as a panda. And when you high-five someone at the finish line, you're a honey badger. Bizarre? Yes. But this is the strange phenomenon called oscillation that scientists found in neutrinos. Much like a human suddenly appearing as a honey badger, neutrino oscillations were unexpected. They're proof that our understanding of the particle world isn't finished. So, today on Even Bananas, let's talk about how experiments study neutrino oscillation. As you can probably guess, neutrino oscillations are a major focus of research at neutrino experiments around the world. Some experiments study oscillating neutrinos from naturally created sources, like the sun or the Earth's atmosphere. We use particle accelerators to create a neutrino beam at Fermilab to have a bit more control over the neutrino types and an excuse to make pew-pew noises. At Fermilab, we have a lot of neutrino experiments that study how neutrinos behave over short and long distances. To explain how our experiments study oscillations at long distances, I'm joined today by Fermilab scientist Anne Norrick. Anne studies... Anne? Anne, you know people are going to see this, right? What are you doing?
I'm oscillating. Hi, friends. I'm Anne Norrick, and I also study neutrinos at Fermilab, which apparently means I'm not allowed to oscillate. I study neutrinos with the NOVA experiment and work with Kirsty on Dune, which will make even better measurements of oscillation in the future.
When we try to measure neutrino oscillation, we're looking to see if the neutrinos change flavor as they travel. To accomplish that, some of our experiments use two neutrino detectors.
This means we measure our particle accelerator neutrinos just after we make them in what we inventively call a near detector to make sure we really know what we're starting out with. And then we measure them again at a distance to see if they have changed their flavor.
The NOVA experiment is making some of the world's most precise measurements of neutrino oscillation, using neutrinos from Fermilab's NUMI beam and a two-detector system. Roughly 1 kilometer away on the Fermilab site sits the near detector, 100 meters underground. It's made of 300 metric tons of plastic, mineral oil, and scintillator. Sections a bit light up as particles interact in the detector.
The neutrino beam is very dense at the near detector, so we see a lot of particle interactions. We collect data on their energy and flavor. The neutrinos that don't stop in our near detector continue on about 500 miles up to the far detector in Ash River, Minnesota. The whole trip takes them less than 3 milliseconds.
Similar to a flashlight, the neutrino beam spreads out as it travels, so the far detector needs to be much bigger. NOVA's far detector uses the same materials, but weighs 14 metric kilotons and is about the length of a commercial jet. Making both detectors out of the same materials makes it easier for us to compare the neutrino interactions we see.
When the neutrinos get to Minnesota, we check to see how many of them have oscillated. At the near detector, 99% of the neutrinos in our beam interact as muon neutrinos. But by the time they arrive in our far detector, almost all of them appear as electron or tau neutrinos.
And that's not a coincidence. We build our far detectors where we expect lots of neutrinos will have changed their flavor. In our marathon analogy, if you wanted to see a human change into a honey badger, and who doesn't, you'd stand wherever the math says is optimal honey badger zone.
It's very difficult for us to find tau neutrinos in our detector because tau leptons are really heavy. Most of the neutrinos in our beam don't have enough energy to make a tau lepton, so to us, they're pretty much invisible. But NOVA can see electrons created by electron neutrinos that have appeared in the beam through oscillation. So that's what we look for.
NOVA's main goals is to see if neutrinos oscillate differently from antineutrinos by comparing measurements from a neutrino beam and an antineutrino beam. So far, there are some hints that they might be different, but we need a lot more data before we can be sure. In the future, we're planning to get loads more information about neutrino oscillation from the Deep Underground Neutrino experiment. Dune is the next generation neutrino experiment that will be hosted at Fermilab. Like NOVA, Dune will have a near detector located at Fermilab. That's the part I'm working on. And Dune's far detector will be 800 miles away at Ray Davis's old stomping grounds, what is now the Sanford Underground Research Facility in South Dakota.
DUNE will have 4 FAR detectors, and each one will be roughly the size of the NOVA FAR detector. These detectors will be filled with liquid argon, giving incredible resolution, so we can see the particles produced in the neutrino interaction to within a few millimeters. We're also building a completely new neutrino beam for DUNE, which is going to be the most intense high-energy neutrino beam ever made. The combination of a really dense beam with enormous detectors means we'll get a lot of great data.
Thanks, Sam. I can hardly wait for us to learn even more details about what's really happening in neutrino oscillation. And who knows, maybe even discover why the universe exists. But I'll leave that for a future episode. That's it for today. Let us know in the comments which neutrino fact surprised you the most.
Okay, so yeah, they have a lot of nice videos on neutrinos, Fermilab. So you can go check out this series if you are interested in neutrinos. They have a lot of explanations. You can see them. But I wanted to show you this to illustrate the fact of how the oscillations are actually studied. So as I mentioned, the handle we have on neutrinos as they are is the flavor, because we know that how certain what because different flavor neutrinos take part in different reactions. So by looking at what kind of reactions the neutrinos taking part in, we get an idea of what is its flavor, right? And from that we can kind of discriminate between electron versus muon neutrino, whereas the mass eigenbasis is not really accessible to us. So based on already existing measurements, you kind of get an idea of, okay, I'm sorry. Okay, give me just one sec. Let me. Yeah, okay. So yeah, as I said, the handle we have is for, it's the handle we have in experiments is the flavor of the neutrino, whereas the mass is not accessible to us. But there are already some measurements of what could be the mixing angles and theta and so on. So based on that, we know, for example, you can see that if delta m squared is known, and if we know what is the energy, or we have guessed for delta m squared, we know what is the energy with which we are preparing a neutrino beam, then L is the main deciding factor, right? So you can decide that where is the probability, for example, where is this oscillation probability the maximum, which means that what is the maximum probability for me to see the electron neutrino I started with become a muon neutrino, right? So that's why the lengths are decided based on that. The lengths are decided based on, okay, I've prepared a beam of electron neutrino, I've prepared a beam of muon neutrino. If I wanted to transform into was the optimal length at which I can see it possibly have this oscillation property. And from that, we can even further tighten our delta m squared. So that's why the far detector is so big also, because the beam spreads out. As she said, it's like a flashlight where the light spreads out. There's a beaming of the light as you go ahead. So that kind of beaming happens for the neutrino also. So the far detector is really huge. So the experiment that they have been talking about, the future experiment they're talking about is DUNE. So DUNE is a neutrino experiment which is planned to be at Fermilab, where there'll be a near detector at Fermilab itself and a far detector which will be 1,300 kilometers away. And so you can see that whatever beam you prepared, after 1,300 kilometer, what happens to it. And you can see that the primary science objectives of DUNE are to investigate neutrino oscillations. And as we saw, this mixing matrices tell us a lot about what is a CP violation. So CP violation in the lepton sector could tell us why the universe is made of matter, because remember that CP violation is directly linked to what is called baryogenesis. We discussed this in the very early videos. Um, Apart from that, yeah, what is the ordering of neutrino matrices? Study of the neutrino sources, like the astrophysical sources from which neutrinos are emerged, and other kinds of things. So I think this is set up to come into action next decade or so, 2030s. But yeah, let's see what happens with funding and other things. Okay. So now we can, as usual, solve some questions. Before we solve questions, I'm just going to get some water. So just give me just 2 minutes. I'll be right back. Okay. Uh, Hi everyone. Okay. So let's since we have now discussed neutrino oscillations in some detail, Let's now solve the questions for today. So as usual, I'll give you some minutes and you can try putting your answers in the chat. I'll just monitor the chat from my phone. Okay. Okay. First question. Parameter that captures CP violation in the weak sector, insensitive to the basis of quantum states. Okay. Someone says A. Okay, we can go to the answer maybe. Okay, someone else is answering. I'll wait for a minute. Okay, let's go to the answer then. Yeah, okay, no problem. So the answer is actually A. So I also discussed this in the first part of today. Basically, the Yarlskog invariant is formed from taking the area of different unitary triangles that you can form by imposing the unitary condition on the CKM matrix. So because the CKM matrix has to be unitary, that comes down to a bunch of equations. And from those equations, whenever A plus B plus C is 0, it just is the same as saying you're forming a triangle in complex space. So the area of that triangle turns out to be an invariant quantity. It's not depending on the frame or on the system in which you are measuring the CP violation, whether that's from quark mixing or from those K meson transformations we saw in the first week's lectures, first or second week lectures. So the Yarlskog invariant is a basis invariant way to classify this CP violation. Okay. Next question is related. So those of you who know, please try to answer. The area of a unitary triangle is 7 in some units. What could be the sum of the areas of all unitary triangles? Okay, someone says C. Okay, maybe I'll go to the answer. So the answer is again, it is C. So I'll just go back to, yeah. So basically, you can see that this is basically your CKM matrix. From the unitarity condition, you have this matrix equation. Of course, this comes down to 9 equations when you write it down. And there are 6 equations, as you can see, all these zeros, right? There are 6 equations which are just giving the zero condition. So when you have A plus B plus C is equal to 0, that basically tells you, like, if you think of it as a vector equation, basically tells you that you're forming a triangle, right? So these are the unitarity triangles. So now what Cecilia Yarlskog, what she showed was that Cecilia Yarlskog showed that the area of these triangles, the area of all these triangles are actually the same. And moreover, the area of these triangles gives us an invariant quantity, which is basis independent and gives us a measure of the CP violation. So you can see that in our CKM, if we write the Yarlskog invariant in terms of our different CKM metrics parameters, they come out to be like this. You can see that J J is directly depending on sine delta. So obviously sine delta is the CP violating phase. If delta goes to 0, J goes to 0, that means we have no CP violation. So that's why this is a measure of CP violation. Now you can see that area of the unitary triangle, as they told you, is constant, and all the 6 unitary triangles. Again, why are there 6 unitary triangles? Because they come from the 6 0 conditions of the 6 CKM unitarity, CKM matrix if you impose unitarity, right? So if you take the 6 times the area of the triangle, you get 42. So that's why the answer is the area of all the unitary triangles is 42, because we just saw that there are 6 unitary triangles and all of them have the same area. Okay. Okay. Next question. In which of these situations is particle oscillations not observed? Okay, someone says A. So maybe we can go to the answer. Uh, yeah, so this is the answer when the particles in question carry different charges. Is the answer, because oscillation comes from, right? So oscillation in the sense that one neutrino oscillation, right? That means that I can write this in terms of two different a mixing matrix in the form that we've set up. So that is why the neutrinos themselves have this mixing characteristic, and that's why electron neutrino can become muon neutrino and so on. So that is the idea here. Okay. So basically, I am able to write each flavor of the neutrino. I'm able to expand it in terms of this. Right. I don't know if we call it oscillation in terms of quark, because it's a little different as to what we are doing. But yeah, I think that's why this is the idea where this is I don't know if CP violation is needed for the particular oscillation itself. That's the other thing. Okay. Yeah, I don't know if you call it oscillation, like if you have an up quark like traveling, you don't really see it transform to a down quark or something like that. So I don't think that kind of oscillation is what we do. When you say oscillation, you mean this kind of situation. I think that is the idea. Uh, I can just check if this is correct. 1 second. I'll just check if this is correct, if I made any mistake. Hmm. Mhm. Um, Yeah, I think, yeah, this is the answer. So I don't think CP violation is needed for oscillation, because as you saw, the main thing that was needed is delta M to be different between the different cases. So CP violation itself is not needed for oscillation. But yeah, so that's the idea. The basic thing is, if the electron, muon, and tau neutrino had different charges, then their base you could not express. Yeah, basically the basis would not be so clean. We couldn't write it in, like, the eigenbasis of mass basis like that, because we would have to worry about the charge conservation as well. Because charge conservation plays a role. Okay. Next question. So this we'll discuss after the questions. I have something about solar neutrinos, so you can check this. So basically, MEV neutrinos are produced in the sun, and sun is very far away, but still we don't observe them in the fast oscillation, regime, which means that we should see so many oscillations that it should be averaged out and some property should be seen. We don't see that kind of behavior. Why is this? Okay, someone has answered. Yeah, so the answer is that there is matter effects in the sun. Basically, when neutrinos are produced in the sun, we'll discuss this after. I have some slides on this after the questions. But basically, when neutrinos are produced in the sun, it's different to when neutrinos are produced in vacuum. If they are produced in vacuum, they travel with all the stuff that we mentioned. But when they are produced in sun, they basically may interact with the particles in the sun itself, because the sun itself is made of many electrons and other things, right? It's a dense medium. So through that process, their probability of oscillation is different. So whatever we predict may not be exactly what we are seeing. So that is the matter effect in the sun, and we'll kind of look at this more in detail in the towards the end of the class. Okay. Is there a question? Fine. Next question. Which of these can be determined by experiments on neutrino oscillations in vacuum? Is there a question? Yeah, okay. Yeah, please go ahead. Okay, I'm not able to hear you if you're talking. Maybe you can type the question. I'm not able to hear you. It's giving some like static kind of noise. So, is anyone else able to hear? Yeah, maybe you can type your question. We are not able to hear you. Someone else says no. Exactly what quantum number is actually changing in this neutrino oscillation? Okay, so it's not exactly that the quantum number itself is changing, right? The lepton number, etc., is the same, right? We don't really talk about neutrino oscillating to anti-neutrino or anything like that, although that has also been a subject of recent research. But right now, when we talk about neutrino oscillation, what we mean is that the neutrino is changing from electron type to muon type to tauon type or something like that. Okay. So the idea is very simple. If you look at the two flavor system, right, then it becomes clear. Basically, you can write electron neutrino as some linear superposition of two mass eigenstates. So if you consider two flavor eigenstates and two mass eigenstates, I'm just going to mute you because the static noise is coming. Okay, just write in the chat because I'm not able to hear you. So I'm just muting you for this time being. Okay, anyway. So if you write two flavor eigenstates and two mass, this is considered two flavor system where we have two flavor eigenstates and two mass eigenstates. Then you can see that you can write in terms of some parameter theta if you want. But basically, electron neutrino is some linear superposition like alpha nu 1 plus beta nu 2. Similarly, muon neutrino is the orthogonal sort of linear superposition that of nu 1 and nu 2 because here we only consider two flavor states, right? So suppose you start off with electron neutrino in at some time t is equal to 0 at some position x, right? And you let it evolve. So then I know that by the Schrodinger evolution picture or Schrodinger equation basically, I know that the evolution is going to be e to the power of minus ht, right? IHT times that state, right? Nu of t, if I want to see how a state psi or state nu is evolving, then that's going to be nu of 0 and it will pick up this extra phase factor e power IHT. And here ht is basically, you can write it in terms of px. And the main point here is because they have different masses, nu 1 and nu 2 have different masses, they are mass eigenstates, they also have different momenta. And because of this, this part evolves differently than this part, right? So because of this, what essentially happens is that initially you started off with some mixture of nu 1 and nu 2, but then eventually as time passes, this picks up a different phase factor and this picks up a different phase factor from the time evolution operator. So the mixture you started with is not preserved as you go to another state. The main problem here is that flavor state and mass eigenstates do not line up. So a flavor state does not have a fixed mass and a mass eigenstate does not have a fixed flavor. So they are both some mixture of each other. So we can only control flavor state. So when I prepare an electron neutrino, say it's 60% nu 1 and 40% nu 2, right? But then after some time, because the 60% has evolved to say 55%, but 40% has evolved to some other percent, right? Which preserves everything. Okay. So let's say this has evolved to now, because of the how it goes, 60% is reduced to 55%, 40% is increased to 45%. So then what is happening is that the mixture I started off with 60-40 is not what I end up with 55-45. So that is no longer an electron neutrino. It's some other flavor of neutrino, which we hear is the muon neutrino because it's only a two flavor system. Either it's electron neutrino or muon neutrino. So here the important thing is what is actually changing. There's no quantum number which is changing. The lepton number, etc., is still the same. The main thing which is changing here is that the state we start off with is some mixture of the mass eigenstates. That mixture is not preserved because these two don't line up. So that is why we see this neutrino oscillation. So if you want to see something like lepton number violation, for example, or lepton number changing through a process, then you have to go to something called neutrino anti-neutrino oscillation, where neutrino is oscillating into becoming an anti-neutrino and so on. So that's also a speculative thing which has been proposed recently by several people, including my advisor. So you can go see some papers on the same. But the classic flavor oscillation, there is no such concept. Okay. Fine. So I hope that answers your question. Okay, cool. So next question is this. Okay, there's an answer already. I'll give one more minute in case there's another answer. Okay, yeah. So there's an answer. I'll go to the answer. So answer is actually A. Basically, this shows the differences in the square of neutrino eigenmasses. So remember, we saw in the formula also, this all depends on delta m squared, where delta m squared is m2 squared minus m1 squared. So it's the differences in the square of the eigenmasses that causes the oscillation. Okay, fine. Next question. Okay, someone says C. Any other answers? Okay, we can go to the answer. So the answer is actually C. It's 2 theta squared. So the way to see this is basically so this is the probability in the two flavor system, right? So here we want to see uh, if the neutrino emitted in one flavor as another flavor. So that corresponds to basically this kind of probability. Basically, probability E mu kind of thing. So here, this quantity usually is called the oscillation length. Delta m squared by 4e is called the oscillation, like the L oscillation kind of thing. So if this is very large, then this whole quantity becomes very small. So basically, this is a very fast oscillation kind of thing. So you can average out this quantity. So basically, it just depends on this. Okay. So sine squared 2 theta in the small angle approximation just becomes sine 2 theta the whole square, which is 4 theta squared. This you just average out. You take the average value because oscillation is too fast here. So you get half here, you get 4 theta squared here. So half into 4 theta squared is 2 theta squared. So that's how you get that answer. Okay. So the answer here is 2 theta squared. And the reason is because we are just averaging out that L by L oscillation kind of term to half. And because we've given small mixing angle, we are using the small angle approximation. Okay. Next question. From the fact that we can measure the oscillations of atmospheric neutrinos, we can conclude that 1 of delta m squared is of which order in EV squared? Okay, someone says A. So remember that the oscillation, as we saw, the probability of oscillation depends on three things, right? It depends on the delta m squared, it depends on L, and it depends on the energy. So here, atmospheric neutrinos means they have a fixed energy, which is around MeV, if I remember correctly. Then you have, they have given you what is delta, what is the length. The length is basically, because it's atmospheric neutrinos, you can take the length to be some, quantity which is representative of traveling through the earth, right? Usually it's taken like 1,000 kilometer, of the order of 1,000 kilometer. So if you put those two values together, you get some estimate for delta m squared. So the value that you get for delta m squared turns out to be 10 power minus 3 ev squared. Okay. So 10 power minus 5 ev squared is also measured, but it's usually measured for 10 power minus uh, yeah, 10 power minus 3 is the answer. 10 power minus 4 is some a rough estimate, but if you actually include the proper averaging and other things, you get 10 power minus 3 to be the answer. So basically, the quantities here are The fact that we see the thing oscillate, that means that we are at the peak of this probability, right? That's what it means. So we know what is E because we know the processes that lead to producing these neutrinos. We know the length because they're traveling to the earth, so we know that it's around 1000 to 5000 kilometers, for example. So from these two quantities we can estimate delta m, and from that we can get the order of magnitude. So this kind of calculation was also done in your class. So I think in one of the lectures, maybe 44 or something, you can go and check out that video and see how it comes in. Okay. So remember, we have two measures of neutrino oscillation delta m squared. One is from solar neutrinos, and the other is from this thing, which is atmospheric neutrinos, from the muons which are produced from cosmic rays and all that stuff. Okay, next question. In two flavor approximation, P E mu is the equal to okay, someone says D. Okay. Okay, so we can go to the answer. Okay, someone says 1 minus PEE, but also the answer is okay. Oh, okay, I'm sorry. I think I forgot to put the answer. Okay. Okay, sorry. The answer is actually A. Okay, I forgot to make a slide for the answer. Give me a second. Basically, the probability that electron stays electron or muon stays muon is the, sorry, by electron I mean electron neutrino. The probability of electron neutrino remaining as electron neutrino or muon neutrino remaining as muon neutrino, both of those probabilities are the same. Because this is a two flavor system, the only other possibility is electron going to muon or muon going to electron, and the probability for both of these is also the same. Okay, I don't know why this is not working suddenly. Okay. Okay, so yeah, that's the answer. Okay, so E mu is equal to mu E, because basically this is a two flavor approximation, so there's only two kind of states that it can end up as. Yeah, 1 minus PEE is also the same, but that's not one of the options, right? So the correct answer is A. Okay. Fine. Next question. This is the approximation that you used while deriving the two flavor approximation. So check it out. Okay, someone says D. Any other answers? Okay, we can go to the answer. So answer is actually D. So remember that in your two flavor approximation derivation, in this step basically, sorry. Yeah, in this step, basically, you use that E minus P is M squared by 2E or 2P, whatever it is. So, yeah, Px is equal to M squared by 2E. This is got by, if you take the relativistic energy momentum expansion, which is E is equal to M squared C power 4 plus P squared C squared whole power half. And then you use the fact that it's a relativistic particle, so the momentum is much greater than the rest mass energy. And if you do an expansion, binomial expansion, 1 plus x kind of expansion, neglecting higher order terms, you will get this answer. Okay, so you can try it out. It's just mathematics and it's also explained in the lectures. Okay. Last question for today. Cosmic rays hitting the air in Jupiter produce neutrinos. Neglecting oscillations, how many muon type neutrinos are made for every electron type? Yes, someone says C. Any other answers? Okay. We can go to the answer. The answer is actually C. Basically, cosmic rays are mostly made of protons and they eventually produce muons. When the muon is produced, it produces a muon neutrino. But muon is not a very stable particle. It will immediately decay into an electron, a muon neutrino, and an electron neutrino. So there's an initial muon neutrino from the production of the muon. Then there's an additional muon neutrino from the decay of muon to electron. So there's two muon neutrinos and there's one electron neutrinos. That's why two muon type neutrinos are made for every electron type. But of course, this ratio is not maintained because neutrinos are oscillating into electron type neutrinos and vice versa. So when we measure the actual ratio, we see some difference, right? At least in Earth. Obviously, the same process happens in Jupiter also. And that's how we get an idea of what is the oscillation length scale and subsequently delta m squared and so on for neutrino oscillations. Okay. Okay, fine. So that brings us to the end of the questions. Before we end, I wanted to talk a bit more about solar neutrinos and the solar neutrino problem. The solar neutrino problem was actually what led us to actually discovering or realizing that neutrino oscillations actually are taking place. So it's good to know about how this process actually evolved, right? So basically, solar neutrinos are the only objects which allow us to kind of look into the solar interior, right? The reason why the sun produces neutrinos is because the sun is supported by gravity, right? And the way it's supported by gravity is through fusion reactions. So it turns out that the fusion reactions that take place in the sun produce a lot of neutrinos. So what people did is that they realized that the sun is producing a lot of neutrinos. So we should be able to detect these neutrinos. And when they tried to detect the neutrinos, the numbers were not matching the expected number of neutrinos that were coming. So then it was realized that some of the neutrinos are actually oscillating into other states. And when we try to account for that, then the numbers were matching up. So in this way, the solar neutrino problem was solved in 2001. So it's a very recent discovery in terms of, physics time scales, right? And it's a very interesting history. So basically, you can see that the baseline between the sun to the earth, the distance between sun and earth, it has an average of 1 million miles or 10 to the power 8 kilometers, 1 million meters kind of thing, 1 million megameters kind of thing. So neutrino energies of about 1 MeV allows probing of neutrino oscillation parameters down to this value, which is not possible by terrestrial means because we don't have that much baseline. So remember that, because length and delta m are both there in the oscillation probability expression, when we measure over larger lengths, we are actually probing into smaller and smaller delta m squared also. Okay. So sun is a pure source of electron neutrino, and we know that the fusion reaction in sun produces specially electron neutrino. So when we observe the number of electron neutrino to be less than what it is, we know that some sort of oscillation has taken place. During recent decades, it has been established that significantly fewer solar neutrinos are observed than what would be expected from theoretical modeling. It's extremely important to find out what extent this discrepancy pointed to new physics rather than astrophysical problem, right? Because the initial thought was not about neutrino oscillations. The initial thought was maybe the way that we understand the model of the sun, the fusion reactions itself is wrong because nobody is going to the sun, so we don't know what's happening. So I'll just tell you a little bit about how we model fusion in the sun and why it's so accurate, and then we can understand about more about why the neutrino oscillations turned out to be the only solution. Okay, fine. So basically, there are two side things of two ways in which in which energy due to fusion is produced in the sun. One is a pp chain where two protons combine to form helium as helium-4, right? Four protons actually combine to form helium-4. And the other case is the CNO cycle, where again four protons form helium-4, but carbon, nitrogen, and oxygen are the sort of catalyst for that reaction. So you can see that up to some temperature, which is around a few times 100 times Kelvin, 100 Kelvin kind of thing. Uh, oh, sorry, this is in terms of 10 power 6 Kelvin. So 100, 10 power up to 10 power 8 Kelvin or so. The PP chain is what is more energetically favorable, whereas beyond that point, CNO cycle becomes no more favorable. So this T solar is the temperature of our sun. So you can see that in our sun, PP chain releases more energy when compared to CNO cycle. So PP cycle is what we'll be focusing on. And the important thing is you can see that there are all these neutrinos that are produced, right? So you can see that there are four neutrinos that come out of every PP cycle. And that's the idea. That is what gives us an idea of how neutrinos are produced in the sun. So one important thing that comes up when we talk about the sun is that, for the proton-proton fusion to happen or hydrogen fusion to happen, you have to overcome the Coulomb barrier, right? So the Coulomb barrier between two protons is, you know that when we bring two protons together, they are going to be repulsive because of their like charges. But if they get close enough, then the nuclear potential, like the strong nuclear force, and here I mean in terms of mediated by pions, the strong nuclear force that's there in atomic nuclei gets over because proton and proton are attractive in a very short distance range, right? But at long distances, the Coulomb barrier is a thing. So it has to overcome the Coulomb barrier, then only it can go to this attractive nuclear potential region. So we know what is the Coulomb potential. It's Z1, Z2, E squared by R. Here obviously Z1 and Z2 are 1. E squared is something like this. So to overcome the Coulomb barrier, we need a really high temperature. So you can see that for PP, the Coulomb barrier comes to around 550 kilo electron volt, which is around 6.4 times 10 power 9 Kelvin. But we know that the sun's energy is only around 10 to the power 7 Kelvin. So how is fusion happening if the sun is not so hot? So one answer is that, this 10 power 7 Kelvin is the not every proton in the sun is measured by 10 power 7 Kelvin, right? That is the most probable speed. But actually, inside the sun, we can consider the particles to be an ideal gas because it's a well approximated by ideal gas. Stars are main sequence stars like our sun are well approximated by ideal gas. So actually, there's a Maxwell-Boltzmann distribution, and maybe there are enough particles in the high energy tail of the Maxwell-Boltzmann distribution that we actually can have fusion. So people have done this calculation as well, that if we rely on temperature alone, there is a close to zero chance for fusion to happen. Because if you actually measure, uh, if you actually measure the Maxwell-Boltzmann probability, so here we have Maxwell-Boltzmann distribution where the peak is 10 power 7 Kelvin, and this is the probability for any Maxwell-Boltzmann distribution. So if you measure what is the probability that this kind of Maxwell-Boltzmann distribution, how many particles have 550 keV as opposed to the peak of 0.86 keV, then obviously it's non-zero because every speed has some probability, but you can see that it's very close to zero. 10 power minus 275 is the probability. But we know that this is actually a very common reaction. It's actually happening enough that it can power the star and it can support the star against gravity. So again, the question comes, how is fusion happening? So the answer is that this happens because of quantum tunneling. Actually, there is very deep quantum mechanics even in the sun. So this is my favorite example to give people, because we kind of learn in physics that quantum mechanics is very much to do with small particles, only below the de Broglie wavelength, only in small regions we have to deal with quantum mechanics. But our own sun cannot shine if not for quantum mechanics. It's only because there is a probability of tunneling through this quantum mechanical barrier, the Coulomb barrier, that the sun undergoes fusion. So this is, if any of you don't know, I'm sure you all know, but quantum tunneling tells you that even when there's a potential barrier, you can see that there is a non-zero probability for particles to pass through that barrier. And it turns out that the probability, if we solve for the Coulomb potential, we solve the probability of quantum tunneling, you get something like this expression. And for PP reaction, this probability gives us a chance of 10 power minus 10. So again, it's not like very probable, but compared to 10 power minus 275, this is much more probable, right? So that means that just the temperature based distribution physics does not give us, but 10 power minus 10 gives us. This is sometimes called the Gamow factor after the physicist George Gamow. And you can also estimate the cross section of this process in terms of something called the astrophysical S factor, and from that you can get what should be the energy for that is released. And finally you get this sort of Gamow peak. Essentially, with energy, you can see that the number of particles decreases in terms of the Maxwell-Boltzmann distribution. So number of particles, the probability of finding a particle with a particular energy decreases if you only look at the Maxwell-Boltzmann distribution. On the other hand, the tunneling is directly inversely proportional to the energy. So you can see that, it's directly proportional to energy because this is minus and in the denominator. This is inversely proportional to energy. So more energetical particles are less probable, whereas tunneling has opposite inverse relation in the sense that it's more probable if it's more energetic, the particle has more probability to get tunneled. So you can see that there is a region where, like for example, here the tunneling probability is high, but the particles are not there. The particle probability is so close to zero. Whereas here there are enough particles, but tunneling probability is not there. So there is a region in parameter space where both these effects are just high enough, and that is called the Gamow peak. And this delta E is where all the maximum number of reactions or maximum amount of fusion is taking place in the star. So we have actually measured all these things we have actually made this model of the sun in the sense of this is happening through quantum tunneling and, parameterized all these cases. So now we can go to applying the solar model to getting an idea of what is the actual neutrino flux, right? So these are experiments that have measured from various different quantities, and this is basically the expected production rates from different quantities. So again, this is pp chain, this is from boron 6 and so on. Okay, so this is the solar neutrino spectrum. You can see that these are the neutrinos energy and number which is produced from BP chain that obviously dominates. And then there are a few other processes which may also contribute to the neutrino spectrum. So the idea is that for two neutrinos are produced each time the fusion reaction occurs. Since four protons are heavier than a helium nucleus, two positive electrons and two neutrinos release a lot of energy to the sun that ultimately reaches the earth as sunlight. So this reaction happens very frequently. These neutrinos escape easily from the sun and their energy does not appear as anything. So these neutrinos are produced with even low energies and the sun gets a lot of heat. Okay. So this is the idea. So we have these neutrinos with different energies that are produced by the sun. And this is from the Nobel Prize lecture of one of the people responsible for solving this issue. Okay. So the issue was that neutrinos are mixing. So this is from an article by John Bacall, who was one of the people involved in the solar neutrino experiment, right? So in 1964, following the pioneering work of Raymond Davis Jr., he and I had proposed an experiment to test whether converting hydrogen nuclei to helium nuclei is the source of sunlight. So the goal was not to measure neutrinos. The goal was, by measuring neutrinos, to confirm if all the fusion reactions, Gamow peak, other things that I mentioned is actually true. So they calculated the number of neutrinos of different energy, like the flux that is expected, and the number of radioactive argon atoms these solar neutrinos would produce in a large tank of chlorine. Okay. So based on this, they kind of tried to measure the number of neutrinos. The first results of Ray's experiment was in 1968. He detected only about one third as many radioactive argon atoms. This discrepancy between number of predicted neutrinos and the measured became known as the solar neutrino problem. Okay, so this was like the neutrinos are now missing. We expect this many neutrinos to come, but only one third of the neutrinos are here. So in 1989, so this was in 1968. In 1989, there was a bigger, more, sophisticated experiment called Kamiokande, which was set up where a detector of pure water was used to kind of stop the neutrinos and measure their interactions and measure the rate at which electrons in the water scattered the highest energy neutrinos emitted from the sun. The water detector was very sensitive, but only to high energy neutrinos. Okay. So this was not sensitive. This was sensitive to all kinds of energies. This was sensitive to high energy neutrinos and basically these kinds of this process. Okay. So here this was kind of looking at PP, which is in the lower energy scale. This boron process you can see happens at much peaks at much higher energies. So the Kamiokande experiment was looking for this kind of experiment, and it confirmed that the number of neutrino events were again they were less than the predicted model of the sun, but the discrepancy was less. So here it was one third, here it was less than that. So it means that we are getting closer to the theoretical value, but still there is no uh, equality that is obtained. So in the following decade, three new solar neutrino experiments deepen the mystery. So there was experiments in Italy and Russia, and you can see that they have different names. So Galax and Sage, they were sensitive to lower energy neutrinos, and from that there was also a larger version of Kamiokande called Super Kamiokande, which also made precise measurements of high energy neutrinos. So basically, high and low energy neutrinos are both missing. None of the numbers match up. High energy neutrinos are also lesser than expected, low energy neutrinos are lesser than expected, but both in different proportions. So again, we understand this today because we know that all these processes are because of oscillation, because the neutrinos are oscillating to different flavors, and because this oscillation is energy dependent, that's why the number of high energy neutrinos and low energy neutrinos detected as missing being different also makes sense, because oscillation itself is an energy dependent quantity. Okay. So the solution was that there was a collaboration of Canadian, American, and British scientists who had solved the neutrino mystery. This is an international collaboration, and they had used heavy water. This is called SNO, the Solar Neutrino Operator Observatory, and they used heavy water to measure the high energy neutrinos in a different way than Super Kamiokande. Okay, so this is a kind of setup that they had where it was submerged in a mine, basically. Okay. So SNO collaboration used a heavy water detector in a mode that is sensitive only to electron neutrinos. So they saw that approximately one third as many electron neutrinos as the standard computer model of the sun predicted were created in the solar interior. Okay. The Super Kamiokande, which is primarily sensitive to electron neutrino, but has some sensitivity to other neutrino types, observed about half as many events as was expected. So here you can see that if you measure only electron neutrinos, you get one fraction. If you measure all high energy neutrinos, if you measure electron neutrinos plus some other neutrino types also, if their sensitivity, you get another value, right? If the standard model of particle physics was correct, then the fraction measured by SNO and the fraction measured by Super Kamiokande should be the same, right? All the neutrinos should be electron neutrinos, but the fractions are different, which told us that um, the fractions being different told us that Super Kamiokande, which was not, which was sensitive to, which had limited sensitivity to other kinds of neutrinos also, it was picking up some other types of neutrinos as well, which is not possible because we are only looking for the high energy neutrinos from the sun, and we know that the PP chain and other reactions only lead to electron neutrinos. So that means that the standard model of particle physics was wrong. Somehow the electron neutrinos were changing their nature when they came to the tank. right? So combining SNO and super Kamiokande, SNO collaboration determined that the total number of solar neutrinos of all types, that is electron, muon, and tau, as well as the number of just electron neutrinos. The number of all types agrees with the number predicted by the computer model of the sun. Electron neutrinos is around a third of the total number of neutrinos. So this was a smoking gun. Basically, the difference between the total number of neutrinos and the number of only electron neutrinos, the missing neutrinos are actually present, but they were in muon and tau neutrinos, which are more difficult to detect, and the detectors were not built to detect those neutrinos especially. But still, in the high energy detectors, there was some sensitivity to them, and that led to these kinds of neutrinos also being up there. So the difference in fraction actually hinted that something is happening to the flavor of the neutrino as it travels. Okay, so next is, yeah, where did the missing neutrinos go? Okay, so the solution of the mystery is that the missing solar neutrinos are not missing. The previously uncounted neutrinos are changed from electron into mu and tau neutrinos, which are more difficult to detect. The muon and tau neutrinos were not detected by Davis experiment with chlorine. They were not detected by Russia and Italy, and they were not detected by SNO. The lack of sensitivity to muon and tau neutrinos is a result that these experiments seem to suggest that most of the expected solar neutrinos is missing. On the other hand, Kamiokande and Super Kamiokande had some sensitivity to muon and tau in addition to their primary sensitivity to electron neutrinos, and that's why they showed larger fractions of the predicted solar neutrinos. But there was still an issue, which was that based on the oscillation length scale, as we saw, when the oscillation length scale is very high, these oscillation effects average out, and we are supposed to see some fast oscillation regime. But this was not what was seen actually. The value that was seen was much higher. So reason was that there's actually a matter effect, as I explained during the lecture, during the question part also. The neutrinos are not produced in vacuum. They are actually produced inside a medium which is very dense, right? The sun. So because of this, the propagation is actually affected. The potential changes. And for this reason, the neutrino oscillation also changes. So in matter, you can see that neutrino propagation is affected by interactions. At low energies, the elastic forward scattering is relevant. Inelastic can be neglected. It can be described by the potentials, these two. Okay. In usual medium, a difference of the potentials for nu E and nu A is due to the charge current scattering of nu E on electrons. Basically, inside the sun, there are so many electrons, so scattering processes happen. And because of these, only the electron neutrinos are affected by this scattering. Okay. You can express this change in the potential in terms of something called the Fermi coupling constant and the number density. So if there's more number of electrons, no number density of electrons, the change in the potential is much higher. Okay, so you can also think of it as like an effective index or a refractive index, because this is kind of like a wave propagation in a medium, right? We talk about refraction in a medium, for example. The same kind of idea applies here as well. So difference of potentials leads to appearance of additional phase difference in the neutrino system, and this gives a refraction length. So because of this, the Hamiltonian changes, and the eigenstates and eigenvalues changes. So the mixing in matter is in terms of these new eigenstates, and the mixing angle is also kind of different. So this kind of dependence is what leads to ultimately the value being, even after we figured out neutrino oscillation, the value was kind of different. The reason for this value being kind of different was because the matter effects were still not figured out, and eventually these were also worked out, and it was it was a three scientists, MSW effect it's called after them. W is Wolfenstein, I don't know the other two names, but they were the people who finally found the exact formulation of the neutrino oscillation problem. Okay, so this is basically how it looks like. So you can see how conversion, non-oscillatory conversion. So this is just how it propagates, conversion plus oscillation. And then here is the oscillation plus small matter effect as well. So you can see the proportions are slightly different with respect to each of the scenarios. Okay, so Even Bananas also has a nice video on the solar neutrino problem. I'll not play it now because we are ending the class now, but you can go and check it out. It's a very nice video. It also explains everything as I mentioned. And yeah, so that brings me to the end of the class. So I hope this was understandable to you. Any questions? Okay, if not, I'll just share the links again where you can find the course lectures and videos. So this is my website where you can find all the lecture notes and videos. So here you go. Yeah, so the references are, you can check all of these references that I showed in the beginning. It's there in the slides. All of these, and I've also put it in the slides. Neutrino physics textbook has a chapter on oscillations, and these are various lecture notes from around the internet, and especially this one has a description of the matter effects. Particularly, this archive paper has the MSW effect in some detail, so you can go and look at it. Apart from that, this is my mail ID. You can mail me if you have any questions. And yeah, you can find the references in my slides. Okay, I'll upload the slide. The reference will be there. Okay. Okay, then thank you very much for joining. If there are no other questions, we can end for today. You can get the references from here. This is a neutrino. This is a textbook that I would ask you to follow. But other than that, you can get the. Okay. Thank you very much. See you next week at the same time. Okay. Bye. Bye.